Good afternoon. What I'll try to do is, now that we're all under the sugar high, we'll try to keep the words down and lots of graphics just to keep it interesting. A couple of weeks ago at ITRC, we were looking at ways of optimizing different things, and one of the things somebody said is we really don't know what we're looking at when we're trying to resolve a lot of these problems. So at the surface, we can actually see ripples in the subsurface soils in bank cuts. We can see the difference in terms of the geology when we're looking at gravel pits. But when we really get down to what we're really trying to solve in terms of coming up with feasibility studies and presumptive remedies, there's a lot that we don't know. And so one of the things that we want to try to evaluate is, looking at what are we really trying to understand? We're trying to understand the characterization. We're going to go into a design, whether it's in situ for dosing and how we're going to do things. We're going to implement it in the field, and then we're going to monitor it. More importantly, is each of these steps are interactive. So we may go all the way down to implement something and realize we need more information. So we need to be able to go back and re-loop back into that. So the case study I was doing today is a little different than what Karen and Marianne presented. It's a very large regional study. And so we'll be looking at some of the conceptual site model issues. Maureen will go into some of the selection of remedy type of things from a vendor standpoint, working with a consultant. And then we'll look at those factors that really influence what the remedy is going to be based upon feasibility studies, pilot studies. So when we look at where we're at, this is a figure that Byron Stone from USGS provided in a paper that we co-authored together. And this is the site that we're going to be looking at. We're really looking at a deltaic sequence. This is in the Connecticut River Valley. And we're really at the distal end. And so looking at deposition, what does that mean? At the distal end, we've got lots of fine-grained sediments going in. So we have fine sands, silts, clays. And more importantly, on this site, we identified that the lake wasn't steady. Nothing that we do is in steady state. So the lake actually rose and fell. And that really affected a lot of the geochemistry on site that I'll get into in a few minutes. As we're going through our conceptual site model, two very important things come to mind. One, here is what the geology is, and two, groundwater. So this is the water table on this particular site. And you see this sort of covers a fairly large area. It's about a square mile. It's 690 acres of this particular site. So Marianne told you about a little 30-foot circle on a postage-sized stamp. We're going to take this to, let's look at a square mile and see what happens with groundwater flow. And how does that influence a lot of the presumptive remedies that we're going to be looking at. One of the things Byron Stone told me was, is this little drumlin right here is we also need to look at ages of things. The drumlin is not Wisconsin drumlin. This is an Illinoisan glaciation drumlin that was present. And therefore, that really influenced how groundwater flows, as well as some of the geochemistry. A little deeper above a lacustrine deposit, and then further down below the lacustrine deposit, we see an entirely different groundwater flow regime. Fortunately, this is not contaminated also. But when you look at our presumptive remedies, we have to know in terms of our assessment and our feasibilities where we're going to be looking. So in this particular case, we're located on top of a hydraulic divide. So why not put our contamination sources right on top of the divide? An excellent location to put things. Things sink very rapidly. This is probably one of the highest vertical flows that I've been able to measure. It's a 1/2 foot per foot. So very steep groundwater flows. That also gets into how we're going to solve the remedy and why some of the geochemistry changes. And we also have a discharge. So we have a vertical upward flow, not quite as fast. So here's the site again, and what we have is a couple releases, but of course, if you put a release on top of a hydraulic divide, you end up having multiple plumes flowing in different directions. Here we have one flowing to the north, northeast, and to the south, which are shallow being about 50 feet deep. Another one flowing to the northeast. Deep in this case was the deepest location, was about 90 feet. Also, why not put your processing metal finishing area on top of the hydraulic divide, so you can get, and also throw in your degreaser at the same time. So you can get VOCs and hexavalent chrome migrating in two different directions. And we'll concentrate predominantly on this discussion on this plume. And these plumes range up to 4,500 feet in length. So we really don't want to try, the first presumption that we have in this is we don't want to remediate 690 acres. We want to do something that's a little shorter than that because it becomes cost prohibitive. So really we need to, in our feasibility studies, understand what's really happening on the fate and transport side of things so that we can understand where we're going to go. So a lot of the things that we did is looking at lithology, and we found that a lot of methods are good, some methods are better than others. And in our particular case, looking at the distal end of the delta, we're looking at a lot of fine-grained sediments. And we really needed resolution, and you'll see in a few minutes why we needed it at 1/10 of a foot. And for all those geologists out there who can get geeked out by drop stones, this was actually pulled out at 90 feet in depth, surrounded by clay, identifying for us as the lower boundary unit, which separated the upper contamination from the lower contamination. ITRC really comes up with some really good documents. This one here is really looking at an explanation in terms of mass flux. And again, our feasibility study went from concentration to mass flux. How can we resolve this problem looking at the mass versus just a concentration-based remedy? And so the plume in these cases started in the 1950s. So we had a lot of time for the contaminant to sorb onto the soil particulates. And in some areas, it actually moved out of the pore space and still has resided in the soils. And then looking at another ITRC document where we can see that when you look at concentrations, can all be the same and our gradients are equal, but our conductivity changes, you can see that the mass flux significantly changes, and therefore identifying where the greatest mass is in order to figure out how we're going to treat those particular zones. So what we did is a lot of high resolution site characterization. In this particular figure, to the left are clays, to the right are the sands. The second column shows vertical hydraulic gradient, with the blue arrow showing upward flow and the orange arrow showing downward flow. Coincidentally, that's where your contamination is, where the two flow boundaries meet. And this is at the recharge. At the discharge area, you'd expect the same thing, and that's exactly what we found. So the contamination is where we see changes in vertical flow, and again, that influences how we're going to treat this particular plume. This was information that we were provided prior to getting involved, and through some of the high resolution. The orange lines are boundary conditions of clay, and clay in our case is inches and not feet. In the middle, we have thousands of parts per billion of chlorinated solvent, specifically TCE here. And what we found was a nice high concentration where we were going to treat, and a boundary condition at the bottom where the greatest concentration was 4.6 parts per billion of TCE. That sounds really good. And we were going to go out and we did our studies and our geochemistry, and we looked at how much oxidant we needed and all those fun things until we went out and did some high resolution site characterization. And again, a cartoon only, but this is PID values from the high resolution. And what you see is that we have a lower boundary condition that all of us use as boundary conditions. And what we found was up to almost 6.5 parts per million of TCE directly below the clay boundary. Nothing that we would have expected. So what we were looking at was 5 feet deeper, having very low concentrations, less than 10 parts per billion. 4 feet or 5 feet above that, having 6 ppm. This was our original treatment zone for our feasibility study and our presumptive remedy. And what we found was this is what we were going to have to treat because we had a vertical upward flow. And if we chase that little clay unit, we actually chase that up to the pit where the chlorinated solvents were actually discharged, and it bifurcated in the overburden as it went down, road under the clay unit. In this particular unit, the depth of the 6 ppm was less than 18 inches. So all of a sudden, we were treating a plume down to 50 feet. We extended that by 5 to 10 feet, saved the client almost $1 million in this particular application by having the information up front, looking at not necessarily a feasibility study from a chemistry standpoint, but looking at the feasibility study of injecting the material and targeting it in situ. And what do I mean by the importance of the 6 inches or 18 inches? These are 2 well screens that we ended up doing based upon the high resolution site characterization. To the left, you'll see that we put a 2-foot screen in, and we have 2,400 ppb of chlorinated solvents of TCE. We put a 5-foot screen, and each point center was identical. So in elevations, each were identical. And we had TCE of 677. So the importance here is, the takeaway is that when we're going out to oxidize this particular plume, if we had used the 5-foot screen to determine how much mass was present, we would have been off by a factor of at least 4. And then we want to put a safety factor on top of that. So very important to understand what is the mass that's present. But yet in another location, even in the same plume, you can sort of see the strength of the plume in this one. This one is much wider. There's much more plume here. So the strength of the plume is greater. This is in the core. This is along the fringe. So you can see here the numbers are similar. So when treating the core, we would have been fine, but treating the outside, not so good. And then we can also do some screening information. This was for the hexavalent chrome plume. What we did is a hatch kit. We just did some field screening in the field. And again, looking at how we put those wells in, you can see in here that, you know, this is 47.5. You can add in the inches below. But you can see this is a very narrow range of less than 5 feet. But yet, if I screened above the pink or below the pink, we would have diluted that sample and not understood the importance of, you know, when we look at the stoichiometric calculations in terms of how much additive do we need to put in. This is really critical in order to understand the success of that. Here's another location. This is what actually got us the job. The former consultant had the well to the left showing 180 parts per billion. We looked at the geology and thought there was a restrictive layer at the bottom, and so we requested a deeper well, and we found 5,100. So in this particular case, the previous consultant said no remediation is required. In this application, remediation is required. And the type of remediations that they were talking about was initially they were going to come in with a reactive barrier, an iron barrier, and they were proposing to put that down to 90 feet over almost 1,000 linear feet of width to try to target this. Just think about the constructability of something like that in terms of a presumptive remedy and the costs associated with that. Boring logs are important. We looked at boring logs a little differently. In this particular case, yellow is coarser grain material. The green is your silts or your fine grain materials in lower K, and the reds are your clays. So now you can see that if you color code the PID and the chrome, and when you look for your information, you really want to be targeting this particular zone, and how we can target that with the presumptive remedy and coming in and understanding the chemistry and the lithology associated with that. The other thing that we found on this particular site, and when we stated at the beginning, we didn't want to treat the whole plume. So we actually went out to the plume and we actually identified that there's a boundary condition. This is the site, 4,500 linear feet. And what we had down gradient was the overburden geology. This was our outwash deposits, the foreset beds. Then we got down into the lower deltaic sequence. And what we found out of this is as soon as that upper deltaic sequence was eroded, the recharge from the wetlands and the rainwater actually created a natural attenuation process such that the contamination on the other side of the boundary disappeared. So we had a natural system that we knew was protective of the downgradient receptor, in this case, the wetlands in the stream. And in this particular case, you can see that there's a brook, which is the apparent discharge location. This plume flows under that brook and discharges to another location, which was controlled by that drumlin that we mentioned earlier. So on that, I'm going to turn it over to Maureen to talk about some of the feasibilities that were done on the site.
Great, thanks, Rich, and good afternoon, everyone. So we're at this phase where you're looking at, different alternatives or alternatives analysis, or you have a presumptive remedy, or maybe you have a pile of data and you're trying to figure out what you want to do with it. Quite often you're going to reach out to vendors. You may talk to Paul or Mike or someone like me, and our job is to provide some input to you to give you an idea of what might be feasible, what a design might look like, at least conceptually, and make it deeper as you get along. But this is really a part of the process where you really need to get into the technological weeds. So to really have an understanding of what's feasible, what you can do, getting your cost analysis from the plus 50 minus 30 down to that much narrower range, you really have to have a lot of understanding of what's going on at your site and really what the options are. Now, Rich is presenting a large, more complicated site. But I think the same lessons can be applied across, somebody has a home heating oil site, do I have access? What's my massive contamination? Where is it? In the same way that Rich is doing in just a larger site, but it's really a lot of the same concepts. And so what I really want to do is just have a few general thoughts. I'll probably, re-emphasize some things that have been discussed already. And then, I'll follow on with some specifics about, the site we're talking about today. So as we get started, we talk about the sweet spots. I think we're all pretty familiar that the higher the concentration, typically you're going to use physical removal. As you get into the mid plume, where maybe some source material, maybe not an apple, but you get into some of the chemical reactions. And then when you get to the lower concentrations, usually the biological type remedies are the most cost effective. And as Mike has gone through that, I think with some good detail and information. But it's not, these are generally presumptively how you may use these technologies, but it's certainly not the only way. But this is generally where you might start. And I think Karen and Marianne did a really nice job in presenting how remedies are also combined. Don't get into a silo. Quite often you want to use a combination of remedies to be able to get the most efficiencies out of each of them. And that's, I think, really what we're trying to strive to do. It's really important to understand what your targets are. So people will say, I have an FS and, well, I'd like to get to, GW1. Well, do you really? Like Rich's site, really? Is that what he's going to do, immediately across the whole site? Probably not. And so this is information that's important. But if you do have a driver like this, it's a redevelopment and I have so much time to get this done to achieve at least some reductions, or am I in a manufacturing site where we're going to be there for a while and monitoring, you may have more tolerances for things to hang around. That really plays into this. And the reason I'm saying this with this slide in particular is, how you're using the technologies is also going to be reflected in what some of the outcomes will be. So if you're, generally looking at a mass reduction or mass removal with chemical oxidation or some other technology, until you remove all of the source, you may still have, concentrations in groundwater. If you really need to achieve some of these low levels, there may be other actions that need to take place, either biological or start considering some of the sorption technologies. You start getting into emerging contaminants, and that's even another, order of magnitude lower that you may be trying to achieve. And just, talking a little bit about the lower end of the spectrum and trying to achieve low target levels, really one of the drivers that impacts that has to do with back diffusion. So if you have a site where you've got heterogeneity, you've got a permeable zone, or you may have some finer grain material, quite often some of your contamination is hung up into this. So if you have a reagent that flows through this pretty easily, but if you don't have a lot of longevity, like chemical oxidants generally don't have the longevity, you may clean this up and then you're going to have the diffusion back from the finer grained into the more permeable zones. Now, Mike had mentioned this too, if you have sufficient natural attenuation to overcome what's coming into this, then you may be fine. But if you're trying to, get to a GW1 standard, you may need to use some other remedy, maybe a biological or or one of these absorption technologies that may set up at the interface and be able to manage that. So these are the things that you need to understand, when looking at your site and really what are you trying to achieve and where are you trying to get. Technology classes have already been identified. I'm pretty much, staying focused on the in situ type applications. Information that we need, the site characteristics, contaminant concentrations, treatment goals, times to, these kinds of things. But just walking through the logic, if you're talking to a vendor, what's the first thing you look at? Okay, what are the contaminants? What reagents are possible? And no one is intended to actually read this, but the whole idea is, what classes of contaminants do you have? What are my options? Is visco an option? Is in situ, reduction an option? It's also important at this point, understand what are the conditions as far as the, the chemistry at the site. Is it reducing? Is it oxidative? Do I have a peat layer and am I thinking about oxidation? What is the site telling you? If you have really reducing conditions, but you're looking at an oxidative process, can I flip it? I mean, we flip systems all the time. We go from oxidative to reductive and back and forth. So it's feasible, but sometimes the sinks may be too much and it may not make a lot of sense. So that's another really critical piece of information. See what the site's telling you, what's happening naturally. Do you want to work with that or are you going to try to shift something over? Application options, you're going to start, okay, what is my access? What am I even going to look at? Am I looking at wells? Am I looking at, direct push, horizontal? So these are things that that we would talk with you about. But I think, more critical, what kind of configuration is, as Rich mentioned, he's got a large site. Are you going to be gridding the entire thing, gridding all these acres? You may, if you have a large site, be looking at, a series of fence lines and let some of the contamination come to that. Or like what Mary Ann showed, you had, a small source area, you really may want to hit it hard and grid it in something in a tighter configuration. So the information that you typically are going to provide your vendors, a lot of things that we've already talked about, but getting into what really important for us is really, what are your expectations? What are your expectations? What do you want to get and by when? An output that you'll typically get, is a starting point. This is all going to be conceptual. What are some of the reagents? What are the volumes that you're going to have? How many injection points? But this is still conceptual. At this point, you have to say, okay, this is the reagent, these are the amounts, this is the volume. Now, how am I going to get it in there? How am I going to get it to where I need it to be? So, in that next step, the question you also have, do I have enough information to really develop that design? And I mean the design, I'm talking about the actual application itself. Because a lot of data that's collected is for site investigation. And so with that, you're looking at liability or risk or what's the extent of my plume. But what we're looking at for a remediation is we're trying to focus on efficient reagent delivery and getting it to the right place. And Paul's going to get into a lot more of this detail. But I did want to share, what we've been involved with more recently. And this gets more critical for us when we're dealing with, some of these reagents that we really have to get a lot of volume and really get the coverage in, to try to get that pore space filled. So it's really critical for us to understand, where the flux zones are. So this design verification process here, we're going to be, we have this conceptual model. We want to refine these assumptions. We want to make sure we can get the reagent volumes in where where they're supposed to be. So, a lot of the techniques that you can use are simple. It doesn't have to be crazy. Even if you have some of the smaller sites, a really good boring log, looking at really small incremental, piece, not like this, the 3-foot section. Let's look at the incremental changes. a water injection test. I know Paul will talk about, mention that, and obviously high resolution methodology. All of these pieces of information can be super helpful. And just quickly here, we've done some internal testing where we took data from 24 sites where we conducted these design verification, and looking at this blind spot analysis, what we found was that in about half of them, we had unidentified hydrogeological conditions. That might be another clay string or clay zone or something that really wasn't expected, or we may have had lower injection rates or didn't get the ROI that we would have expected. Maybe a thicker contaminant zone or more contaminant itself, or maybe we found some utility trench that no one really saw in a figure and wondered why everything went in a different direction. So what did that mean for the design? Well, in essence, probably about 70–75%, there wasn't that much of a change, but in some cases there really were. We may have had significant changes, which may have meant we went from direct push to an injection well or vice versa. But we even had 11%, we had the projects canceled because it just wasn't appropriate. So this just gets how critical this information can be. Now, just getting back to the subject site here, talking about Rich's site and the chromium, the presumptive remedy for a hex chrome is you want to take hex chrome to chrome 3, create this precipitate, and you want to create reducing conditions. So I think that's somewhat straightforward, but you do have a lot of options for how you do that. You can use a molasses, you can use lactate, you can use iron, you can use calcium polysulfide. So there's a lot of different ranges of reagents, and some of the differences may make a difference on how you're designed and how it's actually implemented. And the critical issues for this site was the pH high. Rich will get into some of the detail on that, and clearly the distribution. This is a really large area, and what's the formulation and how best to apply reagents to get the most bang for your buck. At the end of the day, what we found is a reagent mix that had both long and short longevity. Short and extended longevity was most appropriate because that allowed for setting up a series of lines that you could maintain these conditions for an extended period of time and let groundwater flow through that, and that would be one of the more cost-effective ways to work. Interestingly enough, at this particular site, on the chlorinated solvent side, now normally if I looked at a site that had concentration, say from 6 ppm, but quite a large area had less than a part per million, I'd be looking at, this is bioremediation, no question. But at this site, the conditions are so oxidative, it was almost impossible. Not a lot, no bugs, just nothing. And Rich will describe some of the conditions in a lot more detail. So something where we would have normally gone forward and really looked hard at a bioremediation sort of remedy, even some more ISCO possibly, it really went to ISCO. ISCO was the right way to go. And with ISCO being the path forward, being able to inject in the right places, because there always is some limited longevity of the reagent, and getting it where we need it in the volumes is really critical. And so like some of the slides, Rich has so many slides, and you can see how complicated the site is. But this was also a process where we worked really closely with GZA, and was very iterative, and worked as a team to try to come up with the best solution for the site. So with that, Rich, we'll get back to you.
Thank you, Maureen. So previously we talked about some of the geology. Now we get into some of the geochemistry. Here are some of the factors that I think on any feasibility study that you're going into. These are some of the data that I think are really important related to the geology, the aquifer, the geochemistry, the microbial, and some of the degradation that goes on. As you'll see, we collected a lot of information here, but just take porosity, for instance. If you're trying to do an injection program, effective porosity versus total porosity, you want to be able to evaluate those two things so that you can actually get the radius of influence that you're predicting. And so as we look at how we want to reduce the chrome, and we're talking about the chrome mixed with VOC plume, the other plumes that we talked about to the west, those were predominantly ISCO. And we did have some very good success by being able to specifically target the zones of interest. But when we're trying to reduce chrome, we need to look at a number of things related to how are we going to do it. We're going to follow this reduction ladder itself, and we're going to make sure that we're going to have some of these and get down to methanogenesis at the end. But some of these things, if they're in the aquifer, are going to act as sinks. And if we have those, we need to overcome them. And on this particular site, you'll start seeing what the heck do we actually have out here. So here's the chrome processing line itself. So we actually did a pilot in here to find out whether or not this was going to work. Here's our releases: sulfuric acid, nitric acid, chromic acid, and the degreaser PCE and TCE. So all our good chemists out there, how many of us would expect that the groundwater pH is going to be acidic? Anybody? And how many would predict that it's going to be basic? So a couple of acidic and no basic. So let's find out what we actually had out there. So remember, we have a hydraulic divide. It's a perfect place to put a process line and a degreaser. But this is actually what we have. This is right outside the process line. We had a number of borings and wells. And what we found, and again, this gets into our presumptive remedy and our feasibility studies, but what the heck do we have here? We have our release up here at 30 feet, water tables at 20 feet, so 18 feet water table. And we had a bunch of low pH. And then as we pass through these clay lensers down into the fine sand unit where we was mobilizing right above the lacustrine or a boundary condition, we saw our pH is jumping up between 7 and 9. Not the typical chemistry that we'd expect, nor is it the typical chemistry that we want to try to get a presumptive remedy to work with. So what actually happened here, we have to go back to our deposition. Remember I said that's very important. So how were these soils deposited? They went into the Lake Hitchcock. Lake Hitchcock's level rose and lowered. Those sediments went in. And what we actually had on this site that we were able to find is desiccated clays. So the contaminant actually migrated through the clays, and our assumption is that those clays actually stripped off a lot of hydrogen ions and created more of a basic condition. So we know what we're looking for. We're trying to convert the hex chrome to trivalent and eventually chrome oxide. But more importantly, how are we going to do that? So we're looking to convert the hex chrome. We have this unusual pH issue. So let's forget about this bottom line for now. And then let's start our remedy based upon changes in ORP or EH. So we need to have this geochemical shift. So just to throw a few more nightmares in, remember we were talking about that ladder. So we want to make sure that we're going to get rid of dissolved oxygen in the aquifer. Pretty high. This is normally across the entire site. Our nitrate levels from the releases that we had along with the sulfate. So these are acting as sinks. So we have to make sure that when we go in for our stoichiometric calculations that we need to calculate these things. Our ORP, we could actually map the plume only on ORP. We didn't actually have to take a sample, but we did. So this is our pilot. We actually went into a bench scale study with a number of products. And what we were looking for is something that was going to both reduce the chrome groundwater quality as well as the VOCs and have some longevity to it. And so we looked at a couple different products. We found, this product here. We also ran a pilot with molasses, and we found that in order to put molasses, we would have needed 4 to 5 times the amount of carbon as a source material to make it work, which was going to make a whole lot of material to be injected. And we identified a number of wells. Then what we did is we calculated what kind of volume that we needed to inject in order to effectively get the radius of influence. And what we calculated is that we needed about 2,100 gallons per point. And what we actually injected was 2,700 gallons. So this gets into, can I really target the area that I want, understanding the feasibility nature of it, and can I get it to where I want it to get? So we started this in 2008. We've been monitoring it for 11 years. What we found is that we've had continuous methanogenesis. So here the groundwater velocity is only 35 feet per year, very slow. So it's been able to self-replicate itself within the aquifer. So that's given us a lot of information that this has longevity. It's going to last for a while, and we can put that in our presumptive remedy. Here's what we found in the data. So by doing all the understanding of the geology and the chemistry, you know, within about 40 weeks, we saw the hexavalent chrome disappear to the chrome 3, and then at about 107 weeks, we no longer had chrome 3. So we figured we were at the, you know, chrome oxide stage. You can see ORP did drop when ORP fell below the line that you see here. The chrome dropped out. But as I indicated before, we got rid of pH initially, and you can see why. pH really didn't change very much. There was a little blip change, but pH is not one of those factors we're going to change. So you have to keep that in mind as you're going through. There are certain things in the aquifer that you're just not going to be able to change. And again, here's the shift change in the pH diagram. So here's our plume. Goes in two different directions from the release itself. By putting in the monitoring wells very accurately using the high resolution site characterization only within the plume, you can then create great groundwater contour maps. And if you do it right, your groundwater contour map and your plumes overlay. Now, I'm not going to take all credit for this, but it's a pretty cool diagram. So what's happened is that we need to understand what we're trying to solve. We've got a lot of flux moving through in terms of mass. And so we really want to target the mass. And by targeting the mass, we're hoping that the rest of the plume is going to decay. So here is our target in the central portion of the plume itself. So by understanding where the lithology is, the top and the bottom, we're able to come up with a nice opaque map that shows the thickness of the plume. And what we did is really coming up with an understanding that we had 17 feet in the pilot. We reduced these down to 15 feet radii or 30 feet on center. And then we separated the data. We knew the effective seepage velocity. We knew that if we allowed it to flow for 8 years, we could have put separation between the two of these by 280 feet. What we did is we left a distance of 80 feet because we wanted to get to some resolution sooner than later. And we injected sodium lactate to basically acclimate, sort of stop the reduction process. The 3DME was really the long-term polymer that actually lasted a very long time to get the long-term success. And so we basically created these as barriers, both here and up by the release area. So we actually treated 5 acres using 155 points. And the thickness was anywhere between 10 and 29 feet. More importantly, when we get down into the presumptive remedy and we get back into cost, which is always one of the important things to our clients, is that if we had actually gone out and did these on 30 feet on center on a 5-acre area, we would have actually needed 1,230 points. So we were able to treat this plume for a fraction of, just over 10% of the total points in order to try to resolve the plume. So what happened? These are the injection points. So we also wanted to look at it from mass. Where was the mass? Because where the greatest mass was, we wanted to look at the stoichiometric calculations and to increase the amount of additive into the plume itself. So what we found was, here was the plume at baseline, and here's the plume about 18 months later. So a very rapid reduction in the plume itself. And in reality, what we found was about 92% reduction at the source area. And the highest concentration there was 51 ppm. So very high concentrations that we were able to reduce. In the core of the plume were, the graphic was a few minutes ago in terms of the thickness of the plume. We saw an 80% reduction in terms of concentrations. And more importantly, down gradient. Remember, if we can cut the head off the snake, we should then understand that that plume is going to shrink. We did not treat anything in the downgrading plume. In fact, this downgrading plume is about 1,500 feet downgrading where these monitoring wells were. So what we saw is that by removing mass, there was a direct correlation with reduction in concentrations downgradient. And again, going back into that conceptual site model again, where we have a high concentrations, the green is the hex chrome plume mixed with VOCs. We have our dividing line where Mother Nature is taking hold. And what we're trying to do is just reduce this mass up here, shrink the plume, and then let the rest of the system go. Therefore, not treating 690 acres, only treating a portion of the site to reduce mass. In the VOC area, what we found is these other things that get in the way is sometimes we get to what's referred to as cis stalling. In our case, we just didn't have cis at all. We had parent materials, so we looked at it based upon Brown's published paper, and we wanted to look at it, do we have abiotic conditions? And what we found was everything upgrading of that magic line where we have lots of recharge, the plume itself was abiotic. So we knew that we weren't going to just reduce this thing because the conditions were so oxidized on this particular site that we needed to go with chemical oxidation. And so once you got below, we got biotic degradation. And so on the TCE, what we had was the plume itself having a high concentration, moving to the northeast. Currently where we're at, in post-injection, we see that, again, similar in terms of reductions at the release in the core, and in the down gradient was also a shrinkage of the VOCs. And so the takeaway here, I think, again, another good ITRC, where if you go out and you do remedial design characterization, that is within the zone of remediation, if you do more work there, your long-term costs are going to be reduced. So I think that's a great takeaway. And then in terms of what do we want to do before I get kicked off the stage, think about your geology, think about your hydrogeology, think about your focused feasibility, not just on the additive, but think about where you're actually targeting that material to go. And if you do all those things together, you'll be very successful. So if you have any questions, please feel to reach out to either myself or Maureen. Thank you.
Great, thank you so much.
So we could probably do a question or two. We're probably burning out a little bit, but does anybody have any question about that site? Oh, come back here and repeat the question.
Yeah, the question was how long was the duration? We're currently at 5 years right now since the injection. The pictorials that I showed you were 18 to 36 months. So very rapid reduction in the chrome, but again, it's expected. I mean, chrome process lines and all those things, this is typical in terms of treatment technologies, but getting it into the aquifer and getting the product to touch the contaminant and understanding where that lithology is key. And then the additive that we put in is working with your vendors, making sure that the stoichiometric volume that you put in is really going to work. And in this case, you can see the results that it was very effective. So we're hoping not to have to go back out there, and this is the final remedy. 4,500 feet. 1,500 feet was from.
Well, that's like a mile, almost.
Yes, yeah, it's 40. The plume's 4,500 feet, but from where we injected on site to the off-site wells was 1,500 feet. So by reducing that mass, the effect is that no more strength of that plume was coming in, and the surrounding lithology and recharge reduced those concentrations. So that was the conceptual model. We had done ecological risk assessments to understand that discharge wasn't going to be an issue, so that the regulators were acceptive in terms of mass reduction followed by long-term M&A.
All right.
Thank you.
With that, thank you.
Oh,
Thank
thank
you.
you.
All right, thank you guys again. All right.